Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the MATH1011 calculus questions from the section on recursively defined sequences and Newton's method. So I've chosen question 2D and question 3E. Question 3 gives us some recursively defined sequences. Question 2 gives us some sequences that are actually explicitly defined. So we'll start with this one here. So we've got a formula here, log of 1 minus 1 on n, written in curly braces. So that tells us we're talking about a sequence here. If we substitute different values of n in, we'll get different values of the sequence. Sometimes we start at n equals 0 for the 0th term. That doesn't make sense here because we can't do 1 divided by 0. And in fact, it doesn't even make sense to start at n equals 1 because we'll get 1 minus 1 in here, which is 0, and log of 0 is not defined. So we'll have to start at n equals 2 to write down this sequence. So let's write down the sequence. The sequence given explicitly by the formula log of 1 minus 1 on n. When n equals 2, we'll get log of 1 minus a half. That's just log of a half. The next term along, when we substitute n equals 3 in, we'll get log of 1 minus a third, so log of 2/3. Substituting n equals 4, we get log of 1 minus a quarter, which is log of 3/4. The next term will be log of 1 minus a fifth, so log of 4/5, etc. So we could continue to write down the terms in this sequence. Now, the question asks us to decide whether the sequence converges, and if it does, to write down its limit. So are these terms getting closer and closer to a number, is the question. We can see the number that we're taking the logarithm of, a half, 2/3, 3/4, 4/5, that number's getting closer and closer to 1. And so it seems like the terms in this sequence will get closer and closer to log of 1, which will be its limit. So let's write that down. Note that as n tends to infinity, 1 on n tends to 0. Hence this term given by log of 1 minus 1 on n is going to get closer and closer to log of 1, and log of 1 is 0. So it seems like the sequence is going to converge to a limit of 0. So therefore, the sequence converges to a limit of log of 1, or log of 1 is 0, so a limit of 0. So that's an explicitly defined sequence there. Question 3E gives us a recursively defined sequence. So it gives us the starting point, it gives us the first term, U1, and it gives us a formula to find each subsequent term. So un plus 1, the n plus 1th term, is the nth term plus 3 divided by the nth term, all divided by 2. So if I wanted to calculate the second term, that's substituting n equals 1 in here. The second term is the first term plus 3 divided by the first term, all over 2. So it's giving us each term in terms of the term before. So this is quite different from an explicitly defined sequence here, where you can just substitute a value of n in. Here we have to build up the sequence, right, from the start. So let's calculate the second term. We know the first term is 1, so it's 1 plus 3 divided by 1 all over 2. That's 4 divided by 2, which is 2. So the second term of our sequence is 2. Let's calculate another one manually. The third term of our sequence is the second term plus 3 divided by the second term, all over 2. That's substituting n equals 2 in here, giving us the third term in terms of the second term. We know the second term is 2 now, so this is 2 plus 3 divided by 2, all over 2. That's 3.5 divided by 2, or 1.75. So we could continue to do this manually, but it's much easier to generate the terms in our sequence just on our calculator. So the way we can do that is we can start by entering the first term in our sequence, which is 1. So press 1 and equals, and then 1 is in the memory of our calculator, that first term. Now, to put this in, this is saying each subsequent term is the term before plus 3 divided by the term before over 2. So I'm going to get the calculator to know what the term before is by pressing the answer button. So now if I say that I want the answer plus 3 over the answer, all divided by 2, when I press that A and S, that answer button, it's recalling the term that was just in its memory, which we know is 1 because we put it there. So now if I press equals, it will give me the result of 2 because it's just calculated the answer plus 3 divided by the answer all over 2. If I press equals again, it now has 2 as the last thing in its memory, so it's going to calculate 2 plus 3 over 2 all over 2 here. Right, so pressing equals again gets us the 1 3/4 or the 1.75 for the third term. Now if I press equals again, I will get the fourth term. So it will give me 1 41 over 56, which is 1.73214285.7. I'm going to assume it's rounded that and put an approximately sign there. So pressing equals again, we'll get the fifth term is 1.73205.081. So we can already see the first 3 decimal places here, 732, are exactly the same. So it seems to be converging and getting closer and closer to a limit. Now let's just for fun press equals again to find the sixth term. So the sixth term is 1.7320508.08. So already we've got now 7 decimal places that are exactly the same there. Now if I press equals again, actually all those 9 decimal places there don't change at all. We get 50808 at the end here. And if you continue to press equals, you will continue just to get this number here. So it does seem like the sequence converges to this number, correct to 9 decimal places. Okay, and so it seems like that the sequence has a limit. So let's write that down. It looks like the sequence has a limit, and it looks like that limit is 1.73205.808 to 9 decimal places there. Is that 9 decimal places? Yes, I just forgot one here. 0808. Okay, now we can actually calculate what that limit is. So let's just do that. So if we let the limit be L, say, the way we calculate the limit is this. We say that L must equal L plus 3 on L all divided by 2. Right? We can see even here, substituting U6 in, when we had U6 plus 3 on U6 all over 2, we got back exactly the same thing, correct to 9 decimal places. So as we're getting closer and closer to that limit, when we substitute the limit plus 3 divided by the limit over 2, we would expect to get exactly the same thing back. So that's how we're going to calculate what is this actual limit? What is this 1.73205.0808? So let's solve this. Multiplying by 2, we get 2L is L plus 3 on L. Subtracting L from both sides, we get L is 3 divided by L. That's saying L squared is equal to 3. Now, there are 2 numbers that square to give 3, plus or minus the square root of 3. We can see this limit is positive here. So we'll say L is the square root of 3, it's positive, and let's just note since the limit is positive. So if you put the square root of 3 in your calculator, you will see that correct to 9 decimal places, it is in fact this 1.73205.0808 there. So it's a recursively defined sequence. We can easily generate each of the terms in our sequence on our calculator, and just by pressing equals lots of times we can see if it's converging or not there. Okay? And if it does converge, we can calculate the limit if we can solve that equation.